Okay, section 6.4 is exponential growth and decay. So first thing we're going to look at in this section is separable differential equations. A differential equation of the form dy dx, when it's equal to a function of y and x, is called separable. We separate the variables by writing it in this form. In other words, I'm going to divide both sides by f of y and multiply both sides by dx. So there we go. So the dx's cancel here, the f of y's cancel here, and we end up with 1 over f of y dy equals g of x dx. Two sides that now I can integrate. So the solution is found by anti-differentiating each side or integrating each side with respect to the variable. So I know you worked on this last year. Let's do one together. So solve for y if dy dx is x squared y squared, and y is 3 when x is 0. This is called our initial condition. Okay, and this will allow us to find that plus c value. Let's take a look at our steps. First thing to do is to take our function and separate the variables. Typically, we put the y on the left because we want to ultimately get y equals, and the x is on the right. So I'm going to divide both sides by y over 2, or multiply by y to the negative 2, and I'm going to multiply both sides by dx. So now I've separated my variables, and I'm going to integrate both sides. So the integral of y to the negative 2 dy is negative y to the negative 1. The integral of x squared is x cubed over 3. And we put the plus c on the right. Let's just talk about that for a second. If I was integrating this separately, I would write negative y to the negative 1 plus c. And if I was integrating this, I would say, oops, equals x cubed over 3 plus, and I'm going to say c sub 1 because these c's are not necessarily the same. If I subtract this constant from this constant, all I do is create a new constant. And I'll call it c sub 2 for the purposes of this. So I don't need to put a constant on both sides. We don't know what this constant is yet. I might as well combine both constants together. So we only put plus c on one side of the equation. All right, now I'm going to go back and use my initial condition. So I want to find what c is. So negative 1/3 equals c. So, and let's go ahead and do that. Apparently they did not do the work for that. So the initial condition is that when x is 0, y is 3. So plugging that in, negative 3 to the negative 1 equals 0 over 3 plus c. So c equals negative 1/3. Plugging it back into our equation for our plus c, and then solving for y. So this again is negative 1 over y equals x cubed minus 1 over 3. If I switch the signs, multiply both sides by a negative, 1 over y equals negative x cubed plus 1 over 3, and then flipping the equation around so that I have y equals. Okay, they left out a bunch of steps, but I'm sure you can see how we get from there to there. If not, ask me in class. Okay, the solution is valid for the continuous section of the function that goes to the point 0, 3, that is on the domain from negative infinity to 1. So looking at our final equation and knowing our initial condition, this is a rational function. This point 0, 3 is on the domain from negative infinity to 1. So that's the continuous part of this function that this is valid for. Okay, so a couple of laws apply to this differential equation, separable variables work. So the first one is the law of exponential change. if y changes as a rate proportional to the amount present, that is if dy dt equals ky, and if y equals y sub 0 when t equals 0, in other words, initial condition, then y equals y sub 0 e to the kt. Now we can get from here to here by using a differentiable equation by separating our variables. And if you'd like, we can do that in class. But it's much easier for this specific differential to memorize the answer so that you don't have to go through the whole process we just did every time. So the constant k is the growth constant if k is greater than 0, or decay if k is less than 0. Let's take a look. If the interest is added continuously at a rate proportional to the amount in the account, you can model the growth of the account with the initial value problem. So here's our differential equation. Our initial condition is that a of 0 equals the initial amount that is deposited, and the amount of the money in the account after t years fits the model that we did on the previous page. So using that, we can figure out some values here. 500 is my initial amount, so my a sub 0 is 500. 5.3%, and how much will you have 4 years later? So a sub 0 is 500, and our rate of change is 5.3%, or 0.053. Plugging that into our model and using a calculator, we get $618.07. Compounded monthly, if you remember from back in your Algebra 1, and our compounded monthly formula, we get $617.79. Remember that this is the principal times 1 plus the rate over the number of times, and this is n times t. So that n represents how many times during the year do we compound the interest. Since it's monthly, that's 12. All right, half-life is the last one that we're going to look at. Find the half-life with this decay equation. They've given you the equation for half-life. The half-life is the solution to the equation, y sub 0 e to the negative kt. 1/2 is our half-life. We're taking half of the initial amount. So that's what we're trying to solve for. So algebraically, we get e to the negative kt equals 1/2, or negative kt equals ln of 1/2, and t equals 1 over k, ln of 1/2, which equals ln 2 over k. We took the negative sign with the ln 2 and rose that to the power, so we had ln 1/2 to the negative 1, which is ln 2. Note that the value t is the half-life of the element. It depends only on k. So the half-life depends only upon k. We'll do some of these problems and work them out together, but get these formulas down so that you have them in your notes. So the half-life with a constant where k is greater than 0 is just simply ln 2 over k. Again, another good model to have in your bank. That's it.